Hello, good morning. In the last video about lifetimes in Rust programming language, we have seen how to validate references with lifetimes, prevent dangling references with lifetimes, how the borrow checker interprets lifetimes, what is generic lifetimes and how do we use them in functions, what is lifetime annotation syntax, and lifetime annotations in function signature. Here is a small code snippet from the last video. Here we have two strings called string 1 and string 2, and I'm basically trying to use the result after the result goes out of scope, and this would throw me an error. So coming forward, let us see uh, what is it to more think in terms of lifetimes. So here I have a small function. It's called function longest that we've seen before. So I have a lifetime here, which is tick a, and I have two input parameters, that is x and y. Both of them take a reference to a string slice, right? So here I'm saying that my input parameter x has a lifetime of tick a, whereas I'm not specifying what is the lifetime parameter for my input parameter y, and I'm saying the return type will still be tick a. This is true and this will compile because my function is returning only x. My function is not doing anything with the parameter y. So when we talk about lifetime, it is more important to understand how each input and the output parameters is related, their lifetime is related to what the return value is, to what the function is actually doing. This is thinking in terms of lifetimes. There are a couple of other points that we'll cover. That is lifetime annotations in struct definition. We've seen in function before. This is not much different from that. It's just that how do we use a lifetime parameter when it comes to struct, right? So, okay, this is my struct. I say the name of my struct is important except, and after the name of my struct, I mention what is the lifetime parameter for it. And I have to mention this within angle brackets. And my important except has only one field, that is part, and I mention what is its lifetime, that is tick a, right? So the main function here, it basically creates an instance of the important except struct. This holds a reference to the first sentence of a string that is owned by the variable novel. You can see here it is owned by the variable novel, right? So the whatever the data is there in novel that exists before the important except instance is even created. So in addition to that, novel doesn't go out of scope until after the important except goes out of scope. So basically the reference in the important except, that instance, it is still valid. So what this annotation exactly means is that an instance of the important except can't outlive the reference it holds in its part field. Okay, this is how we use our lifetime in a struct. So let us see what is lifetime elision. So basically lifetime elision is our compiler trying to figure out what is the lifetime for each parameter, each function. So lifetime elision, much like the ownership and the borrowing model, can be summed up in three individual rules, three different rules. Okay. Uh, let us see what those rules are. So the first rule says that each parameter gets its own lifetime. Much like how we have how Rust is a strongly typed language and all of its parameters must have a type. Much like that, all of the parameters get their own lifetime, right? And the Rust compiler must check for the lifetimes before it compiles. If the lifetime is not matching, then it will throw us an error. So the first rule says that each parameter gets its own lifetime. And the second rule says that if there is only one input lifetime parameter, then that gets assigned to all the output lifetime parameters. We will see a couple of other examples to understand these better. But anyway, the third rule says that if we have multiple input parameters, but one of them is ampersand self or ampersand viewed self, which means that it is a method, then lifetime of self is assigned to all the output parameters. Okay, let us see one after the other example. So here in this case, so say we have a function called first word, and it takes one input parameter, that is s, which is string slice, and it returns ampersand str. So here we see that we have only one input parameter. So according to the first rule, it says that each parameter gets its own lifetime. So it would become much like this, right? So all my parameters should have their own lifetime. The input s has its own lifetime, and the first word gets its own lifetime, right? Now, the second rule says that if there is one input lifetime parameter, then that will get assigned to the output lifetime parameter. Here, my first word function has only one input parameter, that is yes. So, yes will automatically, whatever the lifetime is for this input parameter, that is yes, then it will automatically get assigned to the output parameter. So, this sentence would much become like this, right? Let us try to take another example and go through the rules of the function. So my third rule would come into place only if I have multiple input parameters, but in this case I have only one input parameter. So my third rule I need not apply. The compiler need not apply the third rule. So I have my longest function. This is a different example. My longest function has two input parameters, that is x and y. So in this case, what happens? The sentence would look like this. My longest function gets an input parameter, which is tick A and tick B. We get tick A and tick B because we have two input parameters, right? Because in the rule 2 does not apply here because we have more than one input lifetime parameter. So my rule 3 says that if I have multiple, then I need separate in lifetime parameters. So I have tick A, tick B for x and y. But because this is a function and not a method, I can't really apply rule 3 here, which is the output lifetime parameter won't be whatever the lifetime parameter is for self, right? So in this case, compiler was able to figure out what exactly was the association of all the input parameters and the return value, the output parameter, with the lifetime parameters. But hence, there's no problem. What lifetime elision basically is that instead of us manually typing lifetime parameter to each of the parameters that we have in our program, which could be very lengthy and hectic and a tedious task, instead of that, because of lifetime elision, my compiler does that for me. How does it do? Based on these three rules that we have discussed. So it follows step by step, trying to see if we can apply rule 1 to our case, or rule 2 or rule 3. When it works through that, it sort of becomes like this, right? When it comes to the end of rule 3, if it is able to figure out what should be the output parameters lifetime based on all the rules, then there's no problem. It does not ask. Compiler has figured this out by itself. But if it is not able to figure out, much like our second case here, then it will ask us, it will throw us an error, and it will ask us what exactly will be the output parameters lifetime here. So basically, we need not tell compiler what is exactly the output parameters lifetime in every case. Instead of that, the compiler will try to figure it out for most of the part by itself. If it is still not able to figure that out, then it will ask us explicitly and we have to mention it. That is how lifetime elision helps us. So the up next topic is lifetime annotation in method definition. So basically, how do we assign lifetime whenever we're talking about method definition? Here what happens is lifetime names of for struct fields. Where am I assigning the lifetime? So I have tick A, first of all, I have tick A, which I have to write with an angle bracket, and I have to write this right after the implementation block, right? We declare and use this lifetime parameter, and that depends on whether they are related to the struct fields are the method parameters in the return value that we have to keep in mind. So I have to write the lifetime parameter after the implementation block and after the name of the method definition, after the name of the method. So basically, lifetime names for struct fields always need to be declared after the implementation keyword and then used after the struct's name because those lifetimes are part of the struct type. So in the method signature that is inside the implementation block, that references might be tied to the lifetime of the references in the structs fields, or they might be independent. So in addition to that, the lifetime elision rules often make it so that the lifetime annotations aren't necessary in method signatures. So this is the format for specifying what is lifetime annotation in a method, right? How do we mention it in a method definition? I have to basically mention it before the implementation block and after the name of the method. So the up next part is, okay, now I understand that I have to specify all of this lifetimes to various parameters and lifetime elision could probably help me out instead of doing this boilerplate coding. Okay, that much is clear. But what if I decide that my parameter wants to live as long as the program is running? What if I want that? Then the static lifetime comes into picture. By using static lifetime, I can say that this particular parameter gets to live as long as the program is running. So how do I mention that? How do I declare that this lifetime parameter is static? That is simply by mentioning tick static, right? Instead of saying that tick A, tick B, I say tick static so that the compiler knows that this particular parameter gets to live as long as the program is running. These are few of the essential topics of lifetimes, the ones that we could not cover in the previous video. Now, as a final frontier, let us see putting all of this together, how does it look exactly? So this is basically how do we put lifetimes with trait bounds and generic type parameters together. We've seen generic types in the previous chapter, right? So here, what do I have? I have the longest function. We are aware of the longest function. I've just made a small change to this longest function. That is, along with my input parameters, that is x and y, I've added a generic type parameter that is an, right? So the longest function, this returns, what does our longest function do? It basically returns the longer of the two string slices. But now I have added an extra parameter and I've called it as an, and this is of generic type t. I've mentioned that, right? And this is returning the string, a string slice. So what is this t? We know that this is, because I say t is this generic type, it can be any type that implements the display trait. So here I've imported display and I'm saying in the where clause that t can be any type that implements the display trait. So because lifetimes are a type of generic, the declarations of the lifetime parameter A and the declaration of the generic type parameter T go in the same list inside the angle brackets right after the function name. So I have my function name here and I am going to say that tick A is the lifetime parameter for both x and y inputs, and for an it is generic parameter whichever can implement the display trait. So I say that will be the T part, right? So the extra parameter that we have, that will be printed using the curly brackets, which is why we need the display trait bound. So we mentioned that in the brackets. So this is how our uh, trait bounds and generic type parameters and lifetimes look together. We've used in a simple code snippet, same as our longest function, which returns either of the longest function. We have written the implementation part here, and we're printing the longest function there, right? So this comes to the end of the lifetimes of Rust programming language. Thank you.